Swayam Prabha. Digital India. Educated India.
Welcome all of you for these lectures on fluid mechanics, and today we will discuss about dimensional analysis and the similarity. I have been following these three reference books, but mostly today I will talk about the Professor Radhakrishnan's books, which is one of the concise on the dimensional analysis and the similarity concept. Now, if you talk about that, I will start with the physical modeling experiments what we have in IIT Guwahati or elsewhere, how we conduct the physical modeling experiment. Then I will talk about the dimensions of fluid mechanics properties, which last class we discussed, but just I have to repeat it. And more interesting things today I will talk about the dimensional analysis of Bernoulli's equations. Okay. Then I will talk about the concept of similarity or similitude, solved examples and summary. Let us look at very interesting study what we have been doing in the fluvial lab in IIT Guwahati. So, one side of the figures, if you look at these Brahmaputra rivers, is big river systems which have the dimensions in terms of the length of the island 6 kilometers, width of the islands 2.5 kilometers. So, huge dimensions in terms of the length and the width of the islands. The discharge is about 10,000 meter cube per second, huge discharge, the particle size, then width of the straight left channel and the right channel. These are the dimensions of real rivers, and we call the dimensions of prototype. So, the real river dimensions, what is that, is given as a prototype dimensions. That is what we reflect in the modeling setups what we have. There we scale down it with a discharge level as well as the geometry level, we scale down it. Like for examples, the length of the island at the prototype level is 6.5 kilometers, but the dimensions what we have put it here is about 1.73 meters. So, that is what is called geometric similarity. So, we scale down the models with a appropriate scale. Similar way also you have scaled down the discharge which is at the prototype level, it is 10,000 meter cube per second, but at the models or the plume levels we tested with a discharge of 10 liter per seconds. So, how to do this type of calculations, what could be the model discharge so that it can represent the flow behaviors at the prototype levels. This is the biggest questions what today will be answered it. And if you look at these two figures, you can see these are the two experimental data or experimental geometries of this river represented for the Brahmaputra rivers. Same way, if you look at that, there are the series of physical models conducted in CWPRS Pune. So, like the Cauchy barrage, if you know it, the Cauchy barrage, these are physical models of the Cauchy barrage, which is a scale down the physical model of Cauchy barrage. Similar way, Indira Sagar Dam 3D models, if you can look it, which is a scale down models here. Same way, the Nandgaon port, Kosi river barrage, backwater at Punam ports and 3D models of these ones. If you look at these models, there are the scale down models from the prototypes. But when you do this, also we try to look other similarities. What are they? That's what today we will discuss it. But this type of experimental setup we conduct before implementing a major projects like the barrage, the dam projects, the port projects, all the major projects before implementing it, which all we tested and try to find out what could be the optimum solutions for these Kosi barrage as well as the Kosi river projects. Like for example, if you can see it, there are the flow lines are there. You can see these flow lines. You can see here there is energy dissipation is happening it. You just see it. There you can see it. If you conduct a physical models, you can really just observe the flow patterns. You can see these flow patterns, how the flow is going on. It's very easy to observe the flow pattern, the streamlines, the vortex formations, all you can see it very closely conducting this experiment. Similar way, if you are looking at how much of energy dissipated just downstream of the spillway or the sluice gates, you can easily find out how these, the eddies, the vortex, the energy dissipations, what is happening it, and after that how the hydraulic jump formations are happening it. All these things we can study it when you conduct series of physical models. Most of the civil engineering projects before implementing the field, we conduct a series of physical modeling tests. Also we conduct numerical models what available today in different commercially or the free softwares. We also conduct the experiment, but I can say that most of the times we depend upon the physical models, because that what gives a lot of the strength or the support to engineer to take the decision, because they can see the visually how the flow behavior is happening it. Like for example of the Kosi barrage, if you look at the flow patterns, all the things we can visualize it with a different flow conditions. So considering this visualizations part, considering the flow patterns to observe, even if in a scale down models, that's what gives a lot of confidence to the engineers before implementing. So I can say there is a two complementing each other, the computational fluid dynamics and the scale models, they are complementing each other. We cannot construct a barrage or the dam without conducting physical models. So both are complementing each other in terms of understanding what will be the flow behaviors, what will be the energy dissipations, all we can understand conducting series of physical models. Now you can have the questions in your mind. Then apart from the geometric similarity, what you can see it, always a scale models have a geometric scale down model, or sometimes also use a scale up models. That means always tell it a 1:10 or 1:100, the scale down models. That means 1 unit of the models representing 10 unit of prototypes, or 1 unit of models representing 100 units of in the prototypes. So we do the scale down models to representing the things. Also sometimes if we also go for scale up models. The models are bigger size than the prototype, but these are very special case. So if you look at this way, we have a lot of applications of the physical models conducted for any major river projects or the dam projects. Now if you look at, before starting this, the topic on similarities, I can say that let us do a small experiment which is called Reynolds number apparatus experiment. which is very simple experiment what was conducted by Reynolds with a color dye facilities, is a dye injectors, and there is a pipe which is a regulated the flow here, and the flow can be conducted with different Reynolds numbers, the flow Reynolds numbers. The flow Reynolds numbers, as you know it, is defined as this way. That means inertia force by viscous force. If I make it that ratios will give say Reynolds number of this. That what as you increase the number of the Reynolds numbers, as is indicated is that if you increase the number of Reynolds numbers, you can see these color dyes are changing it. That means there is a lot of diffusions of color dyes happening it. The flow patterns are changing it. Visually what we are saying it, there is change of the flow patterns. There is change of flow from the laminar to transitions to the turbulent. We will discuss all how it happens using virtual fluid ball concepts, but you can see that with a simple color dye experiments, we can find out at what the Reynolds numbers, the flow changes from laminar to transitions, the transition stage to the turbulent stage. We can identify, and we conduct the experiment with respect to the non-dimensional number of Reynolds numbers. So, that way this is a very simple experiment to find out the threshold of the Reynolds numbers to divide between laminar transitional flow and the turbulent flow. So, more details we will discuss in the next class. Now, let us coming to the dimensions of the fluid mechanics properties. As discussed in the last class, I am just repeating it that you have the dimensions of basic geometry, which in terms of length, area, volume, then comes out the velocity, accelerations and volumetric discharge. That means volume per unit time, that is what the discharge, volumetric discharge, volumetric rate, kinematic viscosity and the strain rate. Similar way, we look at these sides, the dimensions of pressure, stress, viscosity, momentum, flux and torque, power, work and energy, mass flux, this is momentum flux, this is for the mass flux, surface tension and the density. So, I am not repeating these, but just to have the showing you the dimensions of basic fluid properties, what we generally encounter to solve the problems. Now, if you look at many of the times when we derive a big equations, we face a difficulty or we have a doubt over that the equations whatever I have derived it, are they correct? In equations you can have a subcomponents, are they subcomponents are correct? So, what do? We use a dimensional analysis concept to find out the equations what we have derived it, is it correct? Also we can look at that equation derivation at the step by step, that what is the unit or what is the dimensions of each term of the equations. If you evaluate that, then you can check it the correctness of the equations. That is what if you look at these equations, it looks very complexity. Okay. There is a equations which is involved with volumetricals and d by dt, there is a mass flux in and mass flux out. It looks like a very difficult equations. It is having the chance that we will do mistakes in any of the part of the equations. What you do in that case, that you just check the correctness of these equations, substitute the dimensions of each terms like a rho, dv, dv is the volume stands for here, 1 by t is the time, d by dt is 1 by t. So, you get a dimensions of this part. Similar way, this is a mass flux coming in and going out, that is what Bv m by t. So, that way if you look at the each term of these equations having the same dimensions, that means the equation is correct. The same way you can try it, look these ones, This also will have a same expressions. So, we can always look it whenever you have a doubt over a equations which is mostly the lengthy equations, you substitute the dimensions and see that each term of the equations whether have the same dimension or not. If not, then you check it where it is the mistakes. So, that is what in this case the conservation of mass, which look is a very complicated equations, but to know the correctness of the equations we use the dimensions of each term, then find out what is the dimension of each terms, then the part what we look at are they dimensionally homogeneous, that what we tested it. Similar way, this if you look at the linear momentum relationship along the streamwise directions, which looks very difficult equations what we have, we write it from these, the sum of forces is gravity force and pressure force, again we write it this form. It's if you look at there is a differentiations, there is so all these terms if I substitute the one by one the dimensions, like in this case gravity force, this is a unit weight, area, then dz, this is a area, dp, the pressures. Similar way, if I substitute all the terms, if you look at that each terms having a dimensions m into L by T square, which is a force. So, each terms are equating into the force. So, this concept what I introduce for you only, whenever you derive a big equations, complicated equations like there will be a integral part, a differential part, please use the dimensional analysis component to find out are they correct in terms of concept of dimensional homogeneous of this equation. Most of the physical equations are dimensionally homogeneous. Now, the similar way you know it's most often what we do in the fluid mechanics, we use the Bernoulli's equations. Okay. Mostly widely used or widely misused equations which is called the Bernoulli's equations. We discussed a lot about these equations. So, let us have it again look at that in a dimensional analysis of Bernoulli's equations with a derivations part. If you look at the unsteady frictional legs flow along a streamline which is the Bernoulli's equations, it's look it in terms of differentiations, the integrations part and all the things, substitute the dimensions. Finally, we will see it the each terms having the same dimensions L square by T square. Substitute that. I just encourage the students have a this practice whenever you derive the equations, just spend few minutes to write the dimensions of each variables, each term, then check it whether it is a dimensional homogeneous. So, that way you can use the each dimensions and check it, this is what. The similar way you can check these equations also. If there is a mistakes in these equations, you can easily identify when you equate the dimension of each terms, because it is a dimensional homogeneous equations. So, each terms should have the same dimensions, and if you equate it, you will get it same thing. So, if you go for a simple model, this is a what called a very, it is not a complex that much, but we can say it is a that having integrations and all the part. So, but when you talk about a steady incompressed flow, you know the standard Bernoulli's equations in a different forms, and you just substitute it, you will get it the dimensions which is the length dimensions. So, we always use the dimensions to understand it whether there is a correctness of the equations. If not, then we look at where is the mistakes. Not only that, you can also interpret it each term what is it representing it. Like for examples, what I have here is the length, that means it is a as equivalent to a water head, it is a length dimension, it is H equal to energy in terms of water head. That is what we are getting it here. So, the dimensions also speaks out that what type of conservations we are doing it. What we can also interpret it, the physical meaning of these dimensions, what we are getting it. So, looking that part, let us go for the next star, which is the similarity or similitudes approach. That means, in fluid dynamics, when you conduct the experiments, we should have a relationship between full scale or the prototype and a flow with a smaller ones, which is the model. We need to have a relationship between that. That relationship you can use it by conducting the experiment at the model scale, we can take it to the prototype scale. If that is the conditions, either you conduct the experiment with the full scales, as I showed lot of experimental facilities for automobile industry, they do total full scale models. Okay. But many of the cases we cannot go for the full scale models like a dam, which is in generally having the dimensions of 30 meters height, width of 40 meters, more than that. We cannot conduct this type of big experiment, scale experiment in any big setup. So, we cannot do a full scale models for a dam, full scale model for the barrage, but we can conduct full scale models for automobile aerospace industry problems also, but not in the problems which we encounter in civil engineering problems, which have more dimensions. We scale down to models. When you do the scale down of the models, we have to look at the similarity. Is 4 type of the similarities happens it: geometric similarity, kinematic similarity, dynamic similarity and the thermal similarity. So, as we are not talking about energy conservations much more in these lectures, we will focus on these 3 similarity: geometry, kinematics and the dynamic similarity. So, if you look at that part, the first I am talking about geometric similarity. If you look at this is what? The prototypes, full scale. Okay. That is what is the Boeing X-42B. But we cannot conduct these big scale experiments. What we do it, we scale down it, we make it exactly the same in terms of a scale down models. So, that we keep all the angle, the flow direction are preserved it. Orientations models and prototype with respect to surrounding must be identical. So, what do we do it? We do a geometrical similarity with the same linear scale ratio, same linear scale ratio. We apply it and to make it to geometrically the similarity. That is what is the geometrical and similarity models, what exactly you can compare visually, that they are geometrical scale down it. They like the length, the area, the volume, all geometrically scale down it with the angles and all this way. So, and finally, we tested in the wind tunnel facility. That is what the wind tunnel facilities is model is tested in the wind tunnel facility, and whatever the pressure variations, the velocity variations, then we take it from the model to the prototype to design a robust Boeing fighter plane. So, this is what have been doing it with a geometric similarity, but we also to look it should have a kinematic similarity. When you talk about the kinematics, what it says that we have the model, we have the prototypes, this is the prototypes, this is the models. That means, in the model and prototypes should have the same velocity vector, the streamlines patterns. That means, the velocity vectors what we have, the velocity direction, the streamline, and the model should have a scale factors. Okay. We can have a scale factor. So, that the kinematic similar is a homogeneous points, the points what we are telling it, which is a representing in models and the prototypes, that should have a lies at the homogeneous points at the homogeneous times. When same time in time and also in its positions, they should have the same location, same vectors, we should represent it. If it is that, then it is called the kinematic similarity. So, it depends upon the time scale along with the length scale. So, two scales are there, the time scale and the length scale. So, to achieve this, we do a Reynolds number similarity, Flow-Proud number similarity or Mach number similarity. Now, if you look at another problems where we are looking for the what could be the similarity length. Like for example, so we are looking for a pre-surface flow with a prototype waves. This is the wave process may be happening in oceans or the lake, that what we have to represent it in model waves. When you do that, if you look at that, the wave have a characteristics like the height of the wave, the length of the wave, and also you have the velocity vectors. In this case, since it is a free surface flow conditions, Flow-Proud numbers should be equal for model as well as for the prototype. That is what is there. The Flow-Proud numbers of the model and prototype should be equivalent. Then we are substituting the Flow-Proud numbers in terms of velocity and the length. Since we are conducting the experiment on the earth surface, so g does not vary it, the acceleration due to gravity does not vary it. So, you can use the same g components. So, you can get it a relationship between the velocity at the model, length velocity at the model and the velocity and the length of the prototypes. There is a relationship what you get it when you do kinematic similarity. That means, equating Flow-Proud numbers for model is equal to Flow-Proud number of the prototype. So, if you look at these scales, so the Flow-Proud numbers contains the length and the time dimensions, because there is no mass dimensions in that. So, it is a purely kinematic parameter fixes the relationship between length and time scale. If I consider the alpha is a scaling factors between the prototypes and the models, if I use this relationship, I can get the what could be the ratio of the velocity of the models and the velocity of prototypes. With the substituting these equations will be square root of the alpha. Similar way, the time scale will be computed as like this. So, these are very simple calculations can be done it. So, if you look at that way, this is what the prototype scale. After the scaling down the same process, we scale down the length in terms of alpha factors, which is the length of the wave and the height of the waves, but the velocity and the time we have a different scale factors. This is what we computed based on Flow-Proud number similarity concept. So, this is what the time ratios or time scales and the velocity scale as make it. So, most of the times we do these things to compute it what could be the, if this is the length scale, what could be the time scale, what could be the velocity scales, so that we can represent the flow which is the kinematic similarity between prototypes and the model. Let us discuss about the dynamic similarity. This similarity exists when you have the three scale ratios like the length, time and the force should have the same for model and the prototypes. So, the dynamic similarity happens not only this length and the time scale, but also the force scales similar ratio should be there. What do you mean by that? If you have let you have a top problems like this, you have a prototype, you have a gate and flow is passing through gate and having the hydraulic jump here with having a small eddies or vortex formations like this. This is the point where we are looking at what are the force components are there. As you know it, it will be there pressure force component, gravity force component, friction force or the viscosity force component and inertia force component, and each force has the directions component. If you look at this, they should have a balancing, so all these force vector balancing component at the prototype level. If prototype and models are at dynamic similarity, that means the vector diagrams of this force component of the prototypes and the model should be exactly the same. Force magnitudes may be different, but the vector diagrams, vectorical diagrams, the directions and all these component should be exactly same. So, that the force all this component should be exactly same. If it is that, we can make a ratio between forces of inertia force of the model and the prototype, they should be equal. So, if you look at this concept, when it hold good, we call dynamic similarity. To achieve the dynamic similarity, first we should have geometric similarity as well as the kinematic similarity. If you do not have these two similarity, we cannot achieve the dynamic similarity. So, when a dynamic similarities are the same, the model, prototype, force and pressure components are identical. That means their ratio will be the same. So, if you look at this way, the force what is acting it's here, and if you look at this the diagrams of the force vectorical diagrams of model and prototypes, they should have the same. If it is that, you know from the vector calculus, we can compute it what will be the ratio between them. The ratio between them should be equal, otherwise the vectorical additions of these exact similar will not be possible unless otherwise you make it the ratios are the same, the directions and the ratios are the same value. Mostly if you look at this, for the compressible flow we use the Reynolds numbers, Mach numbers, specific heat ratios, but incompressible flow without free surface flow conditions we mostly the Reynolds numbers, but others like numbers also comes, the Reynolds number, flow Proud number, Weber, cavitations number what we discuss can be used for free surface flow. Now, let us derive the relationship between the dimensional analysis and the similarity. As I told from the vector diagrams of the force components, that the dynamic similarities force acting these points are similar. In this case, the inertia force of model and the prototype, pressure force of model and prototype, friction force or the viscous force model prototype should be constant, then dynamic similarity is achieved. In that is the case, so now we can just reshuffle these equations to get it at the model level and the prototype level, we get a one constant. Similar way, we write inertia force and the pressure force, inertia force, we get another constants. So, you are equating, as I said it earlier, we equate the flow Proud number similarity in case of free surface flow. So, similar way we can establish this equation is Reynolds numbers equations, and this is what the Euler equations part, what we can get it by equating this part. Now, just to look it, I am not going to detailed derivations of this part. If you take a fluid element along a streamline, like this is the fluid element, okay, this is the streamlines which is having dx and dn dimensions. You have the shear stress which is changing at this along the nth directions, and you get it what could be the shear stress. Similar way you can find out the pressure variations and all. Then you can compute the force due to the viscosity, that will be the change of shear stress into the volumetric part. That is what if you put it, you get it this part. Just you substitute the Newton's laws of viscosities and all, then you will get this part. Similar way, the net pressure force acting on this, you can see it will be this part. And inertial force computation, which is the in case of the steady flow, mass into the accelerations or
rate of change of the momentum flux. That what the mass and the momentum flux, what you compute it, that along the streamline directions will give us the inertia force components. If you equate it and substitute these values in case of laws of dynamic similarities, the ratio between this part, you can see that these equations comes out to be the Reynolds and these equations comes out to be the Euler's framework, non-dimensional framework. So, basically what I am to tell it that when you go to the element level, we can derive the ratio between inertia force to viscous force, which will comes out to be Reynolds numbers. We can compute it and we will have the same expressions. Similar way, if you are computing the ratio between inertia force to the Euler numbers, which is will be reverse of the Euler numbers, that what also will get it and we will get the expressions of the Euler numbers and the Reynolds number. So, it is quite easy, you can look at the streamline at the element level as well as the gross characteristic levels, we can understand the flow behaviors in terms of Reynolds number similarity or the Euler number similarity. Now, let us come back to examples levels. Let us have a testing of automobiles in a wind tunnel to find the aerodynamic drags, the power required to overcome this drag part. The data is what is given is model width, frontal area, testing velocity, the scale, drag coefficients is given this data. We need to compute the power required for the prototype level. So, since the pressure, the temperatures are given at the standard sea levels, you can find out what will be the density of the air. You can find out what will be the dynamic viscosity of air, which is a function of the temperatures. You can compute it this way. Now, you can have the model width and there is a scale ratio is given for the model width. We can compute it with a width, what could be the dimensions here. The model frontal area, since the length is 1 by 16, the scale is given it, in area we will have a L square, that means 1 by 16, 1 by 16s. So, we use for the area 1 by 16 squares to compute it what will be the model frontal area. We use the dynamic similarities, means the Reynolds numbers of the models should equal to the Reynolds numbers of the prototypes, since the density and the mu, the same air we are using it. So, density and the mu are the same. So, it comes down to this value. So, substituting this, we can find out what could be the model velocity. Then we can compute it what will be required the Reynolds numbers for the models, because we know the velocity, we can find out what will be Reynolds numbers and what will be the drag force of the prototypes, also we can compute it, and power requirement of the overcome this drag force also we can compute it using the power is equal to the force into velocity component. That is what we have used it to compute this part. It is very easy, just you have to have the many equations used to use are very simple equations and you to compute it. Okay. So, like for examples that we do not know what is the equations of this, you just put the dimensions and check it that whether it is a force component. CD does not have the dimensions, the V square, the rho and Fe, you just substitute it, you will get it the force, the dimension. Similarly, the power is energy per unit time, you can use this force into the velocity is will be the power. Let us come to the second problems, which is a flow over a sphere, which is a GATE 2017 questions, which is given a laminar flow, drag coefficients equations, the density, diameter of the sphere is given, velocity and the CF value is given. Then water now flows over a sphere of 200 millimeter diameters under the dynamic similarity conditions to compute the drag force on the sphere 2. If that is the conditions, what you did it in this case there is no free surface, only the flow Reynolds number of model and prototypes would equate it. As it is not given much details about these two parameters, the density and the mu, you can have a basic equations of these ones, just equating the run. And you can have a this model and the prototype should have the same CF value. If that is the conditions, you can easily compute it force and put the active value. So, only you have to try to understand it, what should be the dynamic similarity will be there, whether the flow Reynolds numbers or the flow Proud numbers. Then you look at the force levels, what is the dynamic similarity conditions, like CF1 is equal to the CF2, which is a function of the Reynolds numbers. So, we can find out the what could be the force acting on this. Now, let us come back before concluding lectures that most of the time we would feel boring of the fluid mechanics reading a lot, okay. But many of the times the knowledge of the fluid mechanics help us to understand so complex problems like economy model of a developing city. We can use our knowledge of fluid mechanics to develop economy models for a developing city like Delhi. If you look at this, the red colors are the urban areas. These are real data sets which is prepared by my students. You can see that 1977, what is the red color area, 93, 2006, 2018, and this is a real data of economic growth. But we do not know what is going to happen in 2050, 2100. That is what is the economy models to predict it. To do that, let us use our fluid mechanics knowledge. What type of control volume we have? We have deformable control volumes, as the control volumes are changing it. If you can look at that, control volumes are changing it, both in horizontal and the vertical dimension. Here, there are a lot of flow is coming, it's mass conservations we follow it, either for money or job, the storage and all. There are a lot of transport processes happen in economic models, okay, in microscopic level and macroscopic level. The knowledge what we have, the fluid mechanics, the particles movement, the element movement, all these things also used to develop an economic model. Similar way we look at whether a Lagrangians or the Eulerian frameworks. Eulerian frameworks means we talk about at a bank level. They do not look at individual money, they look at gross. A particular bank is looking what is the total turnovers representing a. So, they do not look at the individual part, but individual level a person is a Lagrangian framework. So, that way if you look at, if you really understand the fluid mechanics, you can solve or you can develop a economy models for a developing city like Delhi. So, please do have a lot of interest on the fluid mechanics. It is not that it is developed, it is just like a, the science has developed such a way that with combinations of experiment, theoretical derivations, the computational techniques, it has come to certain levels that it can also apply many of the fields, and most of the fields are the similar concept we follow it, and that is what my example to show it. If you are a good mathematicians or good fluid mechanics specialist, you can also use the concept of the fluid mechanics to develop economy models and predict what could be the scenario of the economy or what could be the spread area, this red color area for Delhi city for 2050 or 2100. With this, let us conclude these lectures, but just want to show it. If they look at the history of the pipe flow experiment, which started in 1883 with Reynolds, which we so often we used, Poisils and Huygens, okay. Then Julius Westbeck 1845 and von Korman in 1930. So, each one they have contributed for pipe flow experiment so uniquely to derive these equations, and which we so fondly today we are using it and for designing the pipe flows. We will have a more discussion on this in the next class. Let me thank you for this lecture to here.